Hello. We are going to be talking about a whole bunch of things here in these notes, all relating to the Earth's climate and basically what are some factors that affect the climate here on Earth. As you can see, they are topics 4.5, 4.7, and 4.8. Not in Unit 4, but in our weird little, what I'm calling Unit 0. But if you were to look on AP Classroom and watch any of the videos associated with these topics, they would be in the Unit 4 section, topics 5, 7, and 8. So, here we go. Just with some basics to begin with, and we're going to get into detail regarding these things. Weather is a result of changes in the atmosphere. There should not be an S on results there. Climate is basically long-term weather. Air is a fluid. A fluid is something that will flow from an area of high concentration to low concentration, so technically air is a fluid. So in fluids like air, as temperature goes up, density decreases. So there's an inverse relationship. Warm air is less dense than cold air. Things, whether it's air or water, will move from high concentration to low concentration. That's the concept of diffusion. If I spritzed some perfume right here next to me, there's an area of high concentration next to me with all those perfume molecules, and then 5 feet away from me, there's an area of low concentration of perfume molecules. So those perfume molecules will go from high to low, and they will spread, and the smell will move through the room. The sun is the ultimate source of heat and energy on the surface, and the intensity of sunlight is directly related to temperature. The more intense the sunlight, or the more direct the sunlight is on an area of the Earth, the warmer it will be. And we're going to get into details regarding all of these things shortly. So, just real fast, weather and climate. They are two different things. Weather is short-term, what is presently happening in the atmosphere. And that can change in a matter of minutes or even seconds. So currently the weather is cloudy and, I don't know, probably 90 degrees and like 80% humidity. That's going to be different in an hour probably. Whereas climate is kind of the overall idea of what's happening in a region. It's long-term, slow changes. I like this little diagram. Climate is what you expect of an area. Weather is what you actually get. And both climate and weather are going to be affected by the flow of air and how air is distributing heat from one place to another. That's an air current. Ocean currents that are also distributing heat, and different geographic features. And we're going to be getting into all of those things as we proceed. So let's first talk about the sun and solar radiation. So we already know that the sun is the main source of heat, or the ultimate source of heat and energy on Earth's surface. And we're going to be talking about angles of insolation. Insolation is the amount of sunlight or solar radiation that an area on Earth is receiving. So different parts of the Earth will receive different amounts of sunlight. It's pretty easy to figure that one out. A place like the equatorial regions are going to receive more direct sunlight than the polar regions. Therefore, equatorial regions are going to be warmer than polar regions. I'm kind of getting ahead of myself. So please be aware of the fact that Earth is tilted at an angle off of its central axis. That angle is about 23.5 degrees. So what that means is that different areas of the Earth are going to have different amounts of solar radiation, or insolation. Around the equator, there's a very large angle of insolation. There's almost a direct 90-degree, these are the rays of the sun. They're hitting at the equator at about 90 degrees. So a large angle of insolation, which means that the sunlight is concentrated in like a smaller area, which means temperatures are going to be warmer around the equator. And the opposite thing is happening at the poles. There's a smaller or a lower angle of insolation, which is what you're seeing in this diagram over here. The sunlight, because of the curvature of the Earth, the sunlight is no longer kind of hitting at a direct 90-degree angle. The sunlight is spread out over a much larger area. Therefore, there's going to be less heat in the polar regions. So a general rule of thumb here, the higher the latitude, so 90 degrees latitude is either the North Pole, 90 degrees north, or 90 degrees south at the South Pole. The higher the degree of latitude, the lower the angle of insolation. So what that means is that towards the poles, the sunlight is spread out over a vast area. Therefore, it's not warming that area as effectively as it would if that sunlight was concentrated in a small area, like it is at the equator. Time of year also impacts the amount of insolation that an area receives, and we're going to talk about that on the next slide. You can play around with this insolation using a flashlight, and if you have like a ball at your house, like a beach ball or a globe or something like that, if you beam the flashlight right at like where the center would be, where the equator is, you're going to see a small circle of light. That's going to be concentrated sunlight heating that area up. And then if you beam that flashlight at the curve at the top of the ball, that beam of light will be spread out over a larger area, and that would be, less heating from that widely dispersed sunlight. All right, so seasons play a role here. Or seasons are impacted by the angle of the Earth and the angle of insolation. As a pole, we'll say the North Pole because we're living in the northern hemisphere. As a pole is more angled towards the sun, the northern hemisphere, when it's angled towards the sun, will be getting more direct sunlight. Therefore, those are our summer months. So we'll say in June, July, and August, the northern hemisphere is angled more towards the sun, which means the northern hemisphere is receiving more direct sunlight, and it's going to be warmer when there's more direct sunlight, hence summer. At the same time, if the northern hemisphere is angled more towards the sun, that means the southern hemisphere is angled more away from the sun. So they're going to be having a much smaller angle of insolation. The sunlight will be spread over a wider area, so it's going to be cooler. And in the southern hemisphere, it would be wintertime, which is what it says there. This is just a picture here, trying to move myself, looking at the equinoxes, which is when you've got equal amounts of day and night time. High latitudes have a shallow angle of insolation. Most important thing to remember, like you don't need to know when equinox is and all that jazz, but the most important thing to remember is that whatever latitude is directly horizontal to the rays of the sun, which here on Earth, that is 0 degrees latitude, that's the equator, they're going to receive the most solar energy, which means the most direct sunlight, which means the most heating. That's what all of this means. But we have our seasons, winter and summer, based on the way that the Earth is tilted either more towards the sun or more away from the sun. That's what seasons are all about. So kind of putting all of this together so far, we know that different parts of the Earth are going to be hotter than others based on the amount of sunlight that they're receiving. So what does that mean? Well, that means that the air at the equator is going to be warmer than the air at the poles because there's more sunlight at the equator, which means the air at the equator is not only warmer, it's also less dense than the air at the poles. And remember, less dense things are going to rise, more dense things are going to sink. So we have different densities of air based on the temperatures of the air. And temperature of the air is based on the amount of sunlight that an area is getting. And so these differences in density of the air are going to lead to what we call convection cells or convection currents. Remember, convection is basically the process of warm things rising and cold things sinking, or cooler things sinking. And what we end up with are convection cells or convection currents that distribute heat from one part of the Earth to another. So, kind of bringing it all together, the equator receives more direct sunlight, therefore the air temperature is warm at the equator, and therefore air rises at the equator because it's warm, and then that warm air then spreads towards where it's colder, which is going to be towards the poles. So heat is being distributed from the equatorial regions towards the polar regions here on Earth due to differences in temperature and density of the air. And we're going to talk about what these convection cells are. All right, so let's talk convection. This is the key to distributing heat in the atmosphere and distributing heat in the ocean as well. It's all about convection. As I've already said a few times, Earth receives the majority of solar radiation at the equator, which means we have convection currents. We will have warm air moving from the equator towards regions where there's cooler air, which would be the poles, which is what this bullet says right here. And this movement of warm air and also warm water, we're not just talking air, water as well, ocean water is warm at the equator. That movement of air and water is ultimately what's controlling our climate. And what controls our climate? Again, movement of air and water, that's going to affect what biomes are present in different areas, like tropical rainforest, or taiga, or tundra, and so on and so on. So climate is influenced by movement of air and water, and that has an impact on what biomes we can find at different latitudes on Earth. And we're going to get into biomes in Unit 1, I believe. All right, so let's talk about air currents or convection cells. A convection cell basically is where warm air is rising off the surface of the Earth at the equator, and then it moves towards the poles where it cools a little bit and sinks. And so we get convection cells happening at different points here on the Earth's surface. I've got to get a good place for my picture. So we've got 3 convection cells on Earth in each hemisphere. The Hadley cell, the Ferrel cell, and the polar cell. So again, there's 3 in the northern hemisphere and 3 in the southern hemisphere. And that's what you can see on this diagram. The Hadley cells begin at the equator. The warm air rises from the equator, or equatorial regions, rises up into the atmosphere and moves towards the poles where it cools and sinks a little bit. And that's this Hadley cell. So it goes from about 0 degrees latitude, which is the equator, up to about 30 degrees latitude. So that's where our Hadley cell is. The Ferrel cell originates at about 30 degrees latitude, and it goes up to about 60 degrees latitude. And then the polar cell is from about 60 to 90 degrees latitude. So as you can see here, where the air is sinking, that's where we've got cooler, drier air. So where the air is sinking, that's where we can find drier biomes, like deserts. Most of the major deserts in the world are right around 30 degrees latitude, because that's where the air is cool and sinking and dry. Dry air means it's arid, so it's going to be a desert biome. Where the 2 cells meet and air is rising, we get moist and stormy conditions, like what we have here in South Florida. So what you need to know that these are convection cells. They're based on pretty much distributing heat from one location on the Earth to another. And there are 3 convection cells in the northern hemisphere that surround the whole northern hemisphere, and 3 convection cells in the southern hemisphere. And the names of those cells are the polar cell, the Ferrel cell, and the Hadley cell, just reading from top down. One way to think of it, if you go from the North Pole down to the equator, the letters P, F, H, think of it this way: pretty frickin' hot. As we get closer and closer to the Hadley cell, it's getting hotter and hotter. That's just the way I think about it. So those are your convection cells. They are distributing heat from the equatorial regions towards the poles. These convection cells play a huge role in regulating our climate, and also, because they regulate our climate, these convection cells also determine what biomes are found on the planet. So in addition to those convection cells, we also have winds that blow. Wind is basically just defined as air moving horizontally from an area of higher pressure to an area of lower pressure. I just realized how badly I spelled pressure where it says higher pressure. So winds are going to form and move air from a region of high pressure to a region of low pressure, because everything, Earth wants things to be in equilibrium, in balance. And you can see in this diagram, the red arrows are indicating our different major wind belts that we have. And I do want to make a mention that winds are not blowing in straight lines. There's this thing called the Coriolis effect that makes it appear as though the winds are being deflected, either clockwise in the northern hemisphere or counterclockwise in the southern hemisphere. So that's why you can see on this little map here, the winds are not blowing in straight lines. There's not like a perfect straight arrow going from an area of high pressure here at 30 degrees north to an area of low pressure at 60 degrees north. The arrow is not pointing perfectly upward, but rather it's curving or deflected clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. And we'll talk a little bit about Coriolis effect shortly. So winds are based on the different pressure belts that we have on Earth. Wind is going to blow from an area of high pressure to an area of low pressure to kind of keep things in equilibrium. And we do have these major wind belts, which is what you can see here. They're all labeled on the right-hand side. And again, winds are deflected clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. And take a note of the note that's beneath the diagram. Winds are named based on where they originate from, not where they're blowing to. So the westerlies over here, they originate in the west. That's what the name westerly means. You can read through that yourself. All right, so let's talk a little bit about Coriolis effect. So the Coriolis effect is an apparent deflection or turning of an object's path due to the rotation of the Earth. Like what? What does that mean? What that means is that Earth is not a perfect sphere. Earth is kind of like a squashed sphere. Imagine taking a ball and you squish it from the top and from the bottom. Earth is going to bulge out a little bit more at the equator. So the equatorial region is wider than the polar regions, which means the Earth is spinning faster at the equator because, the whole Earth is spinning at the same speed, sort of, kind of. But the Earth is spinning faster at the equator because it has more distance to cover as it's spinning. So what that means is that it seems like objects are being deflected either clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. If you watch this little animation, pretend you're looking down at like a carousel, which is kind of what you're going to be seeing here in this animation. This will show you what the Coriolis effect is all about. So you're going to end up with a red line and a blue line. We're going to pretend that we've got people on this little merry-go-round or the carousel throwing a ball. So let's see if I can get this. There we go. So the red line, like we throw the ball in a straight line. I'm not a pitcher. I'm not throwing a curveball. I throw the ball, if I'm the yellow person, in a straight line, but it looks like it's curving. Like to me, I'm the yellow person. It looks like that ball is curving because the merry-go-round is moving. There's tons of videos that explain more about Coriolis effect, but again, it's basically the apparent deflection. Really what I want you to know is that it seems like wind and ocean currents are turning clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. That's the big thing regarding Coriolis effect. Why can't I move on? And so what you're seeing here on the left-hand picture illustrating what clockwise means in the northern hemisphere and counterclockwise in the southern hemisphere. And so this is important because what it means for the oceans is that we end up with the currents all kind of flowing together, flowing clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. And if I pick the Atlantic Ocean here, the North Atlantic, we get this big circular flow. We have the Gulf Stream current, the Canary current, and the North Equatorial current all flowing into each other clockwise. And this big circular flow is called a gyre. So you've got the North Atlantic gyre here, the South Atlantic gyre here, and again in the south it's flowing counterclockwise. You've got an Indian Ocean gyre, which is in the southern hemisphere, so it's going to be moving clockwise or counterclockwise. South Pacific gyre and a North Pacific gyre. So these gyres are basically just big flows where you've got a lot of currents all flowing into each other, and the gyres flow clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. And they're important because, as you can see in this little map, some currents are warm, as indicated by the red arrows. Some currents are cold, as indicated by the blue arrows, and that's going to have an impact on climate. And you also may hear about the gyres when we talk about the Great Pacific Garbage Patch and all the trash that is floating in the middle of the North Pacific gyre. And this is just another map showing those gyres. So here in the Atlantic Ocean, this is the North Atlantic gyre with some of the currents that make it up. But notice it's moving in a clockwise direction. And then the South Atlantic gyre is moving in a counterclockwise direction. And that's based on, or due to, the Coriolis effect and the way that things are turning in either the northern hemisphere or in the southern hemisphere. All right, that was a lot. So let's talk about how geography affects climate. Geography, looking at formations like mountains. Mountains can have a huge impact on the climate of an area, and that's what we're going to focus on, are mountains, and how mountains can either deflect or stop the flow of air in a region. So what we want to I'm going to focus on is something called the rain shadow effect. And this is just a cool picture looking at how islands can affect the flow of air. All right, let's talk rain shadow. So the rain shadow effect, we're going to use a diagram here. So we've got an ocean over here on the left, and then the land, and a mountain range, and more land. So, things to know, basic terminology. The windward side of a mountain range or something, the windward side is the side that's in the wind, the side that's facing the wind. The leeward side is on the side away from the wind. So that's first and foremost. So you can see in our little diagram, the wind is coming from over here on the left and moving to the right. So the windward side is the side that receives the most wind. All right, So we've got air evaporating from the ocean, and the wind carries that, let's say, moist air from the ocean towards the land. Air goes up the windward side of the mountain, and as it goes up the mountain, it gets higher in altitude. That's what up means. And as that air gets higher in altitude, the air cools off. The air cools and condenses. Once that air and the moisture in the air condenses, it comes down as rainfall. So on the windward side of a mountain, if we're talking about a mountain range that's near an ocean, that side of the mountain tends to be relatively rainy due to this rain shadow effect, because the air that's moving and hits the mountain cools and condenses, and when it condenses, the moisture in the air will come down as either rainfall or snow or some other form of precipitation. So the windward side of the mountain is wet, whereas the leeward side of the mountain is much drier. So what we end up with, the leeward side of the mountain is said to be in the rain shadow. It's much drier, very dry conditions on the leeward side of the mountain. And so mountain ranges and the rain shadow effect are going to affect climate and therefore determine what biomes we can find in certain regions. And so we tend to find more deserty places on the leeward side of the mountains. These are just 4 more diagrams. Some are showing rain shadow effect, some are simple, some are less simple, but just do a quick Google search and you'll come up with multitudes of diagrams showing what rain shadow effect is. But rain shadow effect is one great example of how geographical features can impact climate. And this is a little satellite photo comparing 2 places in Washington State. You've got your Cascade Mountains here in Washington State. Here's your Pacific Ocean over on the left-hand side. So the air from the Pacific Ocean is going to evaporate. The moisture in the air is going to move, or the air and the moisture, is going to move towards the Cascades. And then you can see the city of Packwood, which is located pretty much at the same latitude, the same elevation as Yakima, but it's much rainier, 56 inches of rain versus 8 in Yakima. And then that's the big difference. That's what we're seeing is a rain shadow effect based on the presence of the Cascade Mountains, which is pretty interesting. That side is temperate rainforest biome. The dry side is more of a temperate desert region. It's not like desert dry as in, you know, sand, but it's pretty arid there in Yakima. So to recap everything that I've mentioned, Earth's surface is unevenly heated based on latitude as well as time of year. Uneven heating causes air movement both vertically, that's your convection currents, and horizontally, those are your winds. Coriolis effect is going to impact the flow of air and cause air to blow clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. And geographic features are also going to impact the flow of air and moisture in the air. And all of these things above influence climate and weather patterns, and therefore what biomes we can find where. So that pretty much covers everything in this section on the atmosphere, oceans, and climate. If you have any questions, obviously let me know, and you can read through the pages in your textbook as well. And you can always watch your AP Daily videos on AP Classroom on any of these topics. So that's all for now.